Hello, today we're going to talk about section 9.6, which is all about free energy and connecting that to the process of dissolution. So let's start out by reviewing enthalpy and entropy. Enthalpy, we use delta H, and it refers to the heat change for a process, effectively, for this level of class at least. You can think about it as absorbing heat or releasing heat. So if delta H is positive, it's an endothermic process. And if delta H is negative, that is an exothermic process. Don't forget that breaking bonds is endothermic and forming bonds is exothermic. Let's also review entropy. Entropy is related to the amount of disorder. Now that's a simplification. It has to do with the number of potential arrangements of the particles or the number of microstates. So if there is an increasing number of potential arrangements, then we say that delta S is positive, or we can simplify that as saying it's more disordered. If delta S is negative, then we can simplify that as saying it's less disordered. But really it just has fewer potential microstates, fewer possible arrangements in space if it has a negative delta S. So let's talk about the process of forming solutions. And it all has to do with intermolecular forces, or we can say interparticle forces. The three things have to happen. Solute-solute interactions have to break. Solvent-solvent interactions have to break. And new solute-solvent interactions have to form. So let's now relate that with our enthalpy and entropy. So when you are breaking bonds, that is endothermic. So delta H would be positive. When you are forming, that is exothermic. So delta H is negative. Now, typically when you are breaking apart particles, you are giving them more potential arrangements in space. So that would give it a positive delta S when you're breaking those things apart. But when you're forming new interactions, there will be less potential possible arrangements because they're like hooked together now. So that decreases the entropy. Okay, so now we can relate this to free energy. Free energy is delta G. And if delta G is positive, that means it's gaining free energy, has to take in free energy. That means it's not thermodynamically favorable. And if delta G is negative, it means it's releasing free energy, which means it is thermodynamically favorable. Remember that free energy, enthalpy, and entropy are related through this equation. Delta G equals delta H minus temperature times delta S. If you want your dissolution to happen, you want it to dissolve in a thermodynamically favorable process, we want delta G to be negative. And if delta G is negative, it is more likely to be negative if delta H is negative or if delta S is positive because of you're subtracting this T delta S term. So the forming of the new interactions between the solid and the solvent contributes to the thermodynamic favorability, but the breaking of the solute interactions and the solvent interactions contributes as well. So the overall free energy of dissolution depends on both of those things. You need to be able to figure out the enthalpy of, because all three of these things are happening. If the amount of heat released is more than the amount of heat taken in when the bonds are broken, then that's good. And then if the entropy, if having them split apart is more potential microstates than formed together, then that could again contribute to the thermodynamic favorability of the process. Okay, so let's look at a few applications of this. Which solution would have a greater entropy with all other factors remaining equal? And justify your answer. So we have two solutions, A and B. We have a saturated solution of cobalt hydroxide and a saturated solution of beryllium hydroxide. Now look at these values of KSP. We can directly compare their KSP values because they have the same number of particles. The cobalt 2 hydroxide has 3 total particles, 1 cobalt, 2 hydroxides. The beryllium hydroxide has 1 beryllium, 2 hydroxides. So since I have the same number of particles, I can compare their KSPs. I know that the cobalt 2 hydroxide is going to produce more particles, it's going to dissolve more. So therefore it's going to have a greater entropy because there's more separate particles, there's more potential arrangements in space. So A. Okay, so it says for each one of the following, choose the variable that will be more favorable in solution formation. For solutions to form, we need to break apart the solvent molecules from each other and break apart the solute molecules from each other. So we want those interactions to be weak. Remember, when you are breaking bonds, that is endothermic. So we want them to be weak because we want the positive values to be low. The new interactions that have to form are the solute-solvent interactions. When you're forming new interactions, that is exothermic, so your delta H is negative. So we want those to be strong because we want that to be large enough because it will help delta G be negative overall. Remember, our equation is delta G equals delta H minus T delta S. So for delta G to be negative overall, it really helps if entropy is positive because this is you're subtracting that T delta S term. So an increase in entropy. And we want delta H to be negative overall because that's going to help delta G be negative. And that also means we want the amount of energy released to outweigh the amount of energy taken in when the bonds are broken.